Bismillahirrahmanirrahim. Assalamualaikum warahmatullahi wabarakatuh. So for today's video, we're going to start the new chapter, that is chapter 3, Induction Motor. So from the title itself, for your syllabus, we only cover induction motor. There is no induction generator covered lah. Alright. So the learning outcome. So at the end of this chapter, you should be able to get an overview of construction and types of rotor induction machine. Number 2, to understand the production of rotating magnetic field. And number 3, you should be able to explain the principle of operation, slip speed per phase equivalent circuit. That is the approximate equivalent circuit, power flow diagram, and efficiency of an induction motor. So first of all, why the word induction? Why is it called induction motor? It is because the rotor voltage at the rotor, which later produces rotor current and rotor magnetic field, is induced in the rotor winding, and it's not being physically connected by any wire. In other words, there is no DC current required to run induction machine. Unlike synchronized machine where we need DC current to for the purpose of voltage induction. Okay, so as for introduction, the advantages of induction motor, it is very simple and extremely rugged, low cost and reliable, and minimum maintenance. While on the other hand, if we want to increase the efficiency, we need to sacrifice its speed lah. And number 2, speed decreases with increasing load. In terms of construction, the highlight is on the types of rotor. So as we know, in any machine, the two main parts is the rotor and the stator. So stator is the static part, while rotor is the rotating part. So for induction motor, we have two types of rotor. So as you can see from the figure, it actually differs in terms of how it is constructed lah. So the first type is squirrel cage rotor, and number 2 is wound rotor. So the explanation is, for squirrel, it consists of series of conducting bars laid into slots, carved in the face of the rotor and shorted at either end by large shorting rings. And the conductor looks like one of the exercise wheels that squirrels or hamsters run on. So that is why it is called squirrel cage rotor. While for wound rotor, it has complete set of 3-phase winding that are mirror images of the winding on the stator. Number 2, the 3 phases of the rotor winding are usually well connected, and the ends of the 3 rotor wires are tied to slip ring on the rotor shaft. Number 3, the rotor windings are shorted through brushes riding on the slip ring. So that's the description of each type of rotor lah. Okay, so the main difference, the other main difference between synchronized motor or synchronized machine with induction motor is the existence of air gap. Okay, in induction motor, we have air gap between the stator and the rotor. This is the cross-sectional view of an induction motor. And the outer part is the static part, that is called stator. The one in the center is the rotor. So between the rotor and the stator, we have air gap. Okay, so now in terms of operation, so from the title of the chapter, it is an induction motor. So our input must be electrical while our output is mechanical. So you must, in terms of operation, you must know that electrical input power comes or enters the induction motor at which part? Is it stator or rotor? So for your information, the electrical power, your input power, is injected on stator. So what happened on stator? Three-phase set of voltage, that is your electrical power, input electrical power, is applied on the stator. Okay, when we have three-phase set of voltage, we will have three-phase set of current flowing. So when we have three-phase set of current flowing through the conductor or the winding on stator, magnetic field will be reduced in the air gap, that is between stator and rotor. Okay, and because we have three-phase set of current, that magnetic field is not static. Instead, it is rotating. Okay, the magnetic field at the stator is rotating, and the speed of the rotating magnetic field is called as synchronized speed, ns. So on stator, we have rotating magnetic field that is rotating at synchronized speed. So what happened on rotor? How can this electrical power converted to mechanical power? So on rotor, the relative motion of the rotor compared to the stator magnetic field produces induced voltage. So notice the word induced voltage, that's why it's called induction motor, according to Faraday's law. Okay, so and then when we have induced voltage, we'll have induced torque according to Lorentz law. So as the result, when we have torque, the rotor will rotate, and that rotor will rotate at a speed that is called as rotor speed, nr. So now we have two speeds introduced, synchronized speed and rotor speed. Okay, so when your rotor has rotated, we can say that mechanical power has been produced, or mechanical power has been produced after we have converted the electrical power. So notice down there that the rotor speed, or the speed of your rotating rotor, must be slower than the synchronized speed to avoid zero induced voltage. So in other words, NR and NS must be different, and NR should be slower than NS. So since we have so many speed, so it is better if we can clarify the types of speed in induction motor. So number one, so we go straight directly to the equation. Synchronized speed is also called as magnetic field speed because it is actually the speed of the rotating magnetic field, and the symbol is either NS or NSY NC. Synchronized speed, yeah. So the formula is 120 times electrical frequency over P. P is number of pole. So if you use this formula, the speed that you get is in the unit of revolution per minute. Okay, so I'll explain later how do we convert the speed from RPM to radian per second. Okay, so that is synchronous speed. And then in induction motor, we have another speed called as slip speed and slip. This one, yeah, and slip, that is actually the difference between NS and NM. NM, what is NM? NM is the motor or rotor speed. Okay, motor or rotor speed, it can be either written as NM or NR, and the formula is NS times 1 minus S. So as I've explained before, motor speed must be slower than synchronized speed. So NS is always higher than NM. So the difference between NS and NM is called as slip speed. Alright. Okay. So another formula is slip. Okay, slip is not a speed. It is a ratio. Notice that there is no no speed word lah after that comes after slip. It's just slip. Slip comma S equals to NS minus NM ataupun N slip U divided by NS. So it's a ratio of N slip over NS. So the slip, since the slip is a ratio, so it ranges from 0 to 1. Okay, because the difference or the N slip is smaller than your NS. Okay. So actually the formula for the motor rotor speed just now comes from the third equation. So rearrange this, get your NM. So you have the formula for NM, that is equal to NS times 1 over S. Okay. So all the formulas here, and sync and slip and NM or NR are in the unit of RPM. Okay, while slip is unitless because it's a ratio. Okay. So how do we convert from RPM to radian per second? So just multiply with 2 pi over 60. So if you have slip speed, for example in RPM, you can get the slip angular speed, omega slip, from n to omega by multiplying with 2 pi over 60. Okay, to convert from RPM to radian per second. So the rotor frequency is actually equal to slip times electrical frequency. So now this is the main part. Okay, as we know, every electrical equipment has its own equivalent circuit. So for induction motor, this is how we call it as the approximate equivalent circuit. Okay, this is how the approximate equivalent circuit for induction motor. Okay. First, we have R1 or RS is called stator resistance. Okay, due to the heating of the winding on stator. And then we have X1 or XS, stator inductance here, due to the self-inductance on stator. And we also have R2. R2 is rotor resistance. R2 is here. Later I'll explain why it is combined with slip. R2 is rotor resistance, that is due to the heating in the rotor winding. And we also have rotor inductance, X2, due to the self-inductance on rotor. The explanation is similar with how we construct the equivalent circuit of a transformer. Every losses accounted must be represented. So R represents heating and X represents self-inductance. Okay, so RC is core resistance, because we have core in the induction motor. And XM is magnetizing inductance. Okay, so this is the just like transformer, this branch is called magnetizing branch. Okay, other than before that, so notice that R2 is combined with S. So R2 over S, the combined, they becomes air gap resistance. So after some simplification, so the approximate equivalent circuit of induction motor that you're going to use combines R2 over S, and that represents air gap resistance. Okay, so in terms of voltage and current, so at front here, the front terminal, we have V phase, that is phase voltage. Okay, Y phase, okay, I forgot to explain. In chapter 1, we have studied the relationship between phase and line voltage for Y and delta connected. That is for three-phase system. So for induction motor, your syllabus cover three-phase induction motor. So that's why we need to consider whether it is Y or delta connected, so that we so at the same time we have two parameters lah, V phase, V line, I phase, I line. Okay, for the voltage on the approximate equivalent circuit, this is a per phase equivalent circuit. In other words, each of the parameters, voltage, current are phase value. Okay. So the front one is called phase voltage or phase terminal voltage, and the current, the input current to your induction motor is called as I1 phase, is called as stator phase current. Why stator? Because remember, for motor, our input is electrical, and remember that electrical power is injected on stator. So electrical power will enter through the stator, and mechanical power will end up at the rotor. So I1 is stator phase current, and then I1 phase is diverted into two paths, I0 phase. So I0 phase goes to the magnetizing branch. So I0 phase is called magnetizing branch current, while the current that on the other path, I2 phase, is there is no specific name on it, okay, but it flows through R1, X1J, X2J, and R2 over S. Okay, so usually you'll be asked to calculate the stator phase current, that is your I1 phase or your input phase current that is injected into your induction motor. So how do you find I1 phase? Just assume that this is a typical circuit in your circuit theory subject. So I1 phase, use KCL here. I1 phase equal to I0 phase plus I2 phase. And then I0 phase, use Ohm's law. We know that I0 phase, voltage across RC and SMJ is equal, and also it is equal to V phase. So I0 phase equals to V phase over RC parallel with XMJ. On the other hand, I2 phase equals to the voltage between this point and ground, that is also V phase juga, but over the summation of all four impedances, R1 plus X1J plus X2J plus R2 over S. So this is your I0 phase and this is your I2 phase. So write down your answer in polar. I0 phase with the angle, I2 phase with the angle, and finally you'll get I1 phase with the respective angle. So this is the phase value. Okay, kita will continue with the next part in the second video. Thank you.